So, welcome to lecture 5 on stereoisomerism. So, in this lecture, isomers are different compounds that have the same formula. So, the compound might have different characteristics with the same molecular formula. So, we divide them into two types. One is constitutional isomers, the second is stereoisomers. So, constitutional isomers are molecules with the same molecular formula, but they differ in the connectivity or the constitution. So stereoisomers also have the same molecular formula, but they do have the same constitution or the connectivity, but the arrangement of atoms in space is what differs in them. So understanding spatial arrangement is basically think of it like two images that are mirror images of each other. So those are examples of stereoisomers. So let's try to overview of these isomers. So all the two molecules below that you see here are identical molecules. So both are identical if you consider the number of carbons and the number of hydrogens present in them. Even though they have the same connectivity, they change in their looks or the spatial arrangement. In terms of the spatial arrangement here, both methyl groups are on the top. Here, one of them is on the bottom, one of them is on the top. So these two are examples of stereoisomers. So these are called cis-trans isomers. So we call it cis when they are on the same side. We call them trans when they are on the opposite sides. So the methyl group, depending on where the group that you are looking at, between two adjacent atoms, if they are right next to each other on the same side, then we call them cis isomers. If they are on the opposite sides, we call them trans isomers. So in order to give these compounds unique IUPAC names, we use the cis and trans prefixes. So notice that the name is the same, 1,2-dimethyl cyclohexane, but the only thing that differentiates these two is by using these prefixes cis and trans. So isomers, why do we call stereoisomers? For example, to maintain orbital overlap in the pi bond, so the C double bond cannot rotate freely. Because it cannot rotate freely, so even though both molecules here have the same number of carbons and the same connectivity, they are not identical because these are stereoisomers. Notice again, CH3 on the same side, CH3 on opposite sides. So we call these stereoisomers. So now so let's look at each of these problems and let's see if we can find out if they are isomers or they are constitutional isomers. So let's see if these compounds are either constitutional isomers or stereoisomers or identical structures. So let's start with the first problem. Notice on the first problem, if you look at the plane, it's in the axial position and here it's in the equatorial position. But still, both of them are on the top. So these are identical molecules. Notice that these are just, we have rotated this molecule by 100 degrees to get this structure. So, sorry. So we have rotated this molecule by 90 degrees to get this structure. So these are identical molecules. Let's look at the next one. So notice that here again, above the plane, both are above the plane. And here, one is above the plane, one is below the plane. And both are adjacent to one another. And here also both are adjacent to one another. In here, this OH group is on the same side, on the top. So this is a cis isomer. Here, both OH groups are on opposite side. This is a trans isomer. Notice that this is not constitutional because the number of atoms in all of them are exactly the same. So these are not constitutional isomers. So these are stereoisomers. Next, let's look at the next structure. Notice the connectivity between these molecules. This is a cyclic structure. This is an acyclic structure. So because the connectivity is different, so these become constitutional isomers. Next, again, let's look at this molecule here. Notice that if you look at the molecule by itself, both molecules are exactly the same. So here there is no cis-trans as well. So these are identical molecules. If you look at, there is no change in cis-trans isomerism also. So you can see these are identical molecules. Now here, let's look at the last one. In this one, notice here, these two carbons are on the top. Here one carbon is on the bottom. When you draw a line here, both these structures are on the same side. So this is the trans structure, this is a cis structure, which means that these two are stereoisomers. So this is how you can identify and classify molecules based on their structure and their connectivity. So pause the video right here and try to solve this problem. Here they're asking you, notice that all of them are isomers, stereoisomers. They're asking you whether it is cis, trans or neither. So pause the video right here and try to solve this problem. So what we saw, the cis-trans isomerism is only one type. There are also other important stereoisomeric relationships. So to identify such stereoisomers, we identify what we call as the chiral molecules. So what is a chiral molecule? A chiral molecule or a chiral object is an asymmetric, which means that it's not the same as its mirror image. So which also means they are not superimposable on a mirror image. For example, best example of a chiral object is your hand. If you take your hand and put it in front of a mirror, notice that both of them are not exactly the same. The image formed is not the exact same as that of your hand. It might have been turned or rotated in one another manner, but those are not exact objects. For example, but if you close your thumb and just show your hand as four fingers, then that is an example of. So if you remove the thumb part and look at just your four fingers, that also cannot be a chiral object. One example of thinking about a chiral object is, for example, you could take the example of a cylindrical object, for example, a tissue paper. If you keep tissue paper in front of, if you keep a tissue roll in front of a mirror, whatever the direction you keep it in, both are identical. Both are identical. They look exactly the same. There is no difference between what you get. So these are examples of imposable and superimposable and non-superimposable objects. So you can test whether two objects are superimposable by seeing if they are superimposable. So two objects are identical by seeing if they are superimposable. So this is how we generally clarify chirality. So if the molecule is asymmetric, we call it chiral. If it is superimposable, we call it achiral. For example, if you take the molecule cyclohexane and if you put it in front of a mirror, the structure look exactly the same on either side. So this is an example of an achiral molecule. So chirality is really important in molecules because two chiral molecules are mirror images. Sometimes they generally have identical properties, but they are not identical in their pharmacology. So in terms of their property, the drug properties, they might differ. So visualizing these mirror images of molecules and manipulating them in three-dimensional space is to see if they are superimposable can be very challenging. So I would recommend to use handheld models. So try buying organic chemistry molecular kits. So that would help you in visual aid. So I will show you a website that can do that as well, but try to do it with a handheld model so that you can understand it easily. Let's take an example of a chiral molecule. Let's say I have this molecule here. If you look at it, this is the mirror image of this molecule. So both of them, they do not look identical at all because the problem is when you put it in the mirror, the one right in the front will come in the front, the one in the back will stay in the back. Now, when you try to rotate the structure and keep it as that of the other structure, you would end up with a structure that looks somewhat like this. Notice that this is not the exact same as this structure. Even though if you rotate it to look like it that way, it doesn't look exactly the same. That's the reason why we call chiral objects non-superimposable objects. Right? So non-superimposable objects. So two stereoisomers are non-superimposable images of a given molecule. That's how you can identify as a stereoisomer. So one another way of checking whether a molecule has a chiral center is a chiral molecule is to check its chirality center. So when you have a single atom like carbon, it generally forms a tetrahedral center. So the tetrahedral center contains four different groups attached to it. Then we call that a chirality center. For example, let's take a look at this molecule here, this carbon here. On this side, you have CH3. On this side, you have CH2, CH3. On here, you have a chlorine. and in the dashed part you have hydrogen. Notice that all the molecules that are attached here are different from one another, so you don't even need to write CH3. So let's look at the four corners and let's write down all the ones that are there. So all four of them are unique from one another. Notice that between these two, we do not consider the carbon itself, we consider the hydrogens as well to check whether they are different from each other. So this is how we can differentiate them. Next, the other way we can differentiate is, for example, let's take a look at the other molecule. Notice here, between for this carbon here. For this carbon here, you have on one side CH2. So on here you have CH2, on here you have CH2. So now this is something that you might get confused. So if you notice that if it is identical, then take the next molecule as well to check whether it is the same or not. Here it's CH3, so let's CH2, here it's CH3, here it's CH2 and then CH2 again. So which means that this is a different molecule, this is a different molecule. And you have the third different molecule, and in the dashed part you have a hydrogen. So notice that all four that are attached to that single carbon are unique from one another. So if you have all four connections unique from one another, we call that a chirality center. So we call that a chirality center. Next, again, look at this carbon here. So this carbon has CH2 here and it has CH here. So here it has CH2, here it has CH, on the dashed part it has hydrogen. So all four of them that are attached to the carbon, this carbon here, are unique from one another. That's why it is a chirality center. So this is an important way to identify chirality center. Let's try some more problems so that you can try and look. So let me do the first one here. So let's try this carbon here. Notice how, which one generally would you have a chirality center and how many chirality centers are there. So first thing, always avoid carbons that do not have any connections to any other carbons except for hydrogen. For example, if you look at this carbon, this has two hydrogens that are attached there. So which means that this is not a chirality center. Here two hydrogens are there, not chirality center. Two hydrogens, not chirality. Two hydrogens, not chirality. Two hydrogens, not chirality. Here you have one hydrogen on the bottom. So this is one unique one, second unique one. And on here you have CH2 and CH2. Whichever side you look at it, all of them end up having CH2 itself, which means that this is not a chiral molecule. So notice that there is no differentiation even if you all go on any side, because this is not a chiral molecule. Let's take a look at the next one. Here for this carbon, there are two carbons here again. Remember, forget anyone that has two hydrogens. So we'll remove all these four. Right now, let's try and look at those two carbons that we have written there. Now for these two carbons, what to do? So let's look at each of them. So this is CH2, this is CH, and there is a hydrogen on the bottom. So this is 1, 2, 3, and 4. So there are 4 unique atoms. This is a chiral molecule. This is a chiral center. Next, look at this carbon here. For this carbon here, you have CH2, you have CH, you have OH, and on the bottom you have hydrogen. So which means now this is 1, 2, 3, and 4. So all 4 are unique, which means this is also chiral. So this molecule has 2 chiral centers. So this molecule has 2 chiral centers. So how do you know which ones are chiral centers and which ones are not chiral centers? So one way to do it is by identifying whether you have a specific group on one carbon. So one way to check it is first all single bonded carbons are not chiral. So if they have a single bond, it's not chiral. So which means that whenever you have two hydrogens, then it's not chiral. And the second one, any double bond is not chiral. Any triple bond is not chiral. So any carbon that has double or triple bond is not chiral. So the only ones that are chiral are the ones that are having sp3 hybridization. So and in sp3 you will have to check that all four are different from one another. So only then you can say that those are chiral. For example, let's try the first carbon here. This carbon has, notice that it has three hydrogens, right? If you remember from chapter 2, it has three hydrogens, so which means that this is not chiral. Let's take a look at this carbon now. For this carbon, it has 1, so CH3, 2, CH3. So which means that both are identical, so this is also not chiral. So this is also not chiral. Next, let's take a look at this carbon here. So 1, it has CH2, and here CH2, and here CH3. So notice that these two are CH2, CH2. Let's take a look at the one that's adjacent to it. So this is CH3. Here it is CH2 again. Notice that it is different from one another. So this is CH2, CH2. This is CH2, CH3. So these two are unique from one another. So which means that, notice that there is, in the dashed part, there is a hydrogen here. So there are four unique parts. So this is a chiral center. So how many chiral centers are there here? So we identified that. So the first one, we identified the first chiral center. This is one chiral center. Let's take a look at this one. So CH3 here. Here it has CH2. And on this one you have CH. Notice that it already has three bonds. So it's CH. And there is a hydrogen on the back. So all of them, all four of them are unique from one another. So which means that this is also a chiral center. So this has two chiral centers. So pause the video right here and try to see if this particular molecule has how many chiral centers. So use the same process again. Try to do it for this problem again. Remember, if it has more than, so if a given compound has more than three bonds, so it should have four bonds. So for first thing this, it should have four bonds and four unique bonds. If they are unique and it has four bonds, then that is chiral. So that's when we can say that it's chiral. So pause the video right here and try to solve this problem. So I have given other problems as well. So this is the one that was written in the back one. So try the other three as well. So pause the video right here and try to see if you can identify all the chiral centers in each of these structures. So next let's talk enantiomers. So some stereoisomers can also be classified as enantiomers. So enantiomers are generally the mirror images which are non-superimposable. So are two molecules that are mirror images but are not superimposable. So therefore not identical. So only a chiral compound can have an enantiomer. For example, if you take this molecule and you try to draw its mirror image, you would find it to look somewhat like this. So this is the mirror image of this enantiomer. So notice that the molecule by itself did not actually change. The only thing that changed is the way in which you look at the molecule. So this mirror image that you see here becomes its enantiomer. Next, some stereoisomers can also be, so often it's easier way to draw the enantiomers is to convert its dashes and wedges. So if it has a dash, convert it into a wedge, that becomes an enantiomer. So again, so dash to wedge are all enantiomers. So when you convert the dash, that becomes an enantiomer. So let's take a simple example of a problem and let's try to draw its enantiomers. So amphetamine, which is one of the psychotic ingredients in methamphetamine, is one of the most common prescription stimulant that is used in the treatment of ADHD. So in World War II, it was generally given to soldiers to reduce fatigue and increase alertness. So recently, this has become a big opioid problem. So this is one of the drugs that that pushes people towards hardcore narcotic drugs. So illegal. So let's try to draw the enantiomers of this structure, amphetamine. So the first thing we want to do is let's take this structure separately. So this is the structure that we have. So first way to draw the enantiomer is imagine a mirror to the side. For example, let's say if there is imagine a mirror here, then how would the molecule look? So you would have, so NH2 would come right here. So let's try and draw the structure. So this is the base structure. With this base structure, you would have this structure here, and this would come straight down, and here you would have NH2. So I'll let you understand why this structure is different from this structure when we name these structures. But these two, remember, are different structures. One another example of this is to take a mirror image on the bottom. So what happens if you take the bottom image, then the bottom image will look somewhat like this. So here you will get NH2 and the dash structure. So this is another enantiomer. So one another one is to change the dash to a wedge. So which is generally behind the mirror. So or in front or behind. So whichever one that you want to write it as. So for that one, we draw the exact same structure. Plus, but in place of a wedge, we draw a dashed line and write NH2. So this is the examples. So these three here are enantiomers. So these three are enantiomers of this particular molecule. So in the same way, now pause the video right here and try to draw the enantiomers of these molecules one by one. So take your time, at least try to draw 2 or 3 examples so that you get an idea of how to draw enantiomers. So pause the video right here and try to draw enantiomers of these compounds. So this brings us to the next concept. How do you differentiate between two enantiomers? So one way of differentiating is to name them differently. So the naming is generally done on R versus S configuration. So configuration is in which direction it is in. So R and S are opposite to each other. So which means that if you have a molecule, so here you have a wedge and here you have a dash, which means that any one of them can be R, the other one will become S. So to represent R and S configuration, we use a system called CIP system or Cahn Ingold Prelog System to designate the chirality center either or of the molecule, either R or S. So if the compound has an R configuration at the chirality center, then the enantiomer of that compound will have S configuration. So remember that every molecule will have only one another enantiomer, so that will have the opposite configuration. So how do you name the R and S? So first thing that we do is using the atomic numbers, we prioritize the 4 groups that are attached to the chirality center as 1, 2, 3, and 4. And we arrange the molecules in space so that the lowest probability priority group always faces away from you, which means it's in the back. So the lowest priority group should always be in the dashed line. And third, we count the group priorities 1, 2, 3 to determine whether the order progresses in a clockwise or a counterclockwise direction. So for example, if this is 1, 2, and 3, and 4 is in the back side, so we don't count 4 every time. So we'll check whether if it's in the counterclockwise direction or in the clockwise direction. If it's counterclockwise, the configuration is yes. If it is clockwise, the configuration is R. So one way to exactly understand this is by a handheld model, but I'll try my best in understanding, helping you understand how this structure can be determined. So let's take a simple example. Let's say we have a molecule that looks at here. So the first thing that we do is to prioritize the 4 groups. So prioritization takes the highest atomic number, the highest priority. In here you have the atoms chlorine first, oxygen, hydrogen, and CH2. In terms of the priority, chlorine becomes 1 because this is the largest, oxygen gets the second one because the second largest, carbon gets the third because the third largest, and finally you get hydrogen. What if you have 2 of them that are the same? How would you name these structures? So let me, so this is the structures that we have. So the first thing we want to do is name these structures. So the first one is here, you have chlorine here, oxygen, hydrogen, and carbon. So this is CH2. Notice that it already has 2 bonds, so it becomes CH2. Now take the structures, which is the largest one among them. So the first one goes to chlorine, the second largest is oxygen, the third largest is carbon, and the fourth largest is hydrogen. So we have given the numbers. Now based on the structure that you see, isolate the structure based on just numbers. So just draw the numbers themselves and isolate as a structure. So this becomes 4, 1, 2, and 3. So I already told you that the fourth one should always be in the back. So how would you make it in the back? So we rotate it based on this axis. So what we do here is we take it and we rotate the structure. How will you rotate this structure? So we rotate it by 90 degrees. So we rotate it by 180 degrees. So what we do here is we take the structures and push it onto this side. So how will that do? So just take this entire structure and push it onto that side. When you push it onto that side, just interchange the numbers. So take the same structure. So this is the structure. In the structure, how would you change the structure basically? Take the numbers out and flip the numbers. So 4 goes here, 3 goes to 2's place. So here it becomes 4. So this becomes 1. Here it becomes 3. And here it becomes, here becomes 2. And here becomes 3. Now 4 is in the back, so forget about 4. Now just look at the order for 1, 2, 3 and try to draw a circle starting from 1 and ending at 3. So 1, 2, and 3. Notice that this structure, you have 1, 2, and 3. This structure is anti-clockwise, so the configuration for that chiral center is yes. So R and S are only applied for chiral centers. So we only draw them for chiral centers. Do not draw them for anything else, just draw them for chiral centers. So the second one is to arrange the molecules so that the lowest priority group always faces away from you. And finally, rotate the structure to check whether it is counterclockwise or clockwise. Now, in the same manner, let's try one another problem. So in this problem, let's consider there's a tie. So for example, here we have OH. So we have OH. So here you have OH, hydrogen, carbon and carbon. Notice that these two carbons are exactly the same. So which means that we'll have to check for the priority. What we do when you have two carbons that are the same is you look for the next carbon, the adjacent carbon. And in that carbon, notice that this carbon is connected to two other carbons, but here this carbon is connected to two other hydrogens. So the tiebreaker is the one that gets more carbons, the one that is attached to more carbons. So here, this carbon is only attached to one more carbon. This carbon here is only attached to one more carbon. Here, this carbon here is attached to two other carbons. So now we can say that that's the priority here. So we can give priority to the one that has more carbon attachments. So which means the one that gets the more carbon attachments gets the priority. So which means that this becomes number 2 and here this becomes number 3. Hydrogen is always given the number 4 because remember that there is nothing smaller than hydrogen. So which means hydrogen always gets the smallest number. So this is how you break ties when you have a given structure. Now let's try another one. In this, let's see if we can tie. So notice that this carbon here, this carbon and this carbon, both are carbon and carbon. So we want to break the tie. So let's look at what it is attached to. This carbon is attached to an oxygen. This carbon is attached to a carbon. So all of those are carbons that are attached, but here there is an oxygen. So oxygen is larger than carbon. So for tie breaking, we choose the oxygen side. So which means that this carbon gets 2 and this carbon gets 3. So the priority is always the based on the first point of difference. So whichever becomes the first point of difference, use that as the way to classify them. Now, one another one in Cahn Ingold system is that when you have a double bonded carbon, that carbon is considered as two simple single bonds. So when your double bond is generally counted as two single bonds so that you give more priority. The last one is understanding how to rotate the structure. Remember, when you rotate the structure, always rotate it based on the axis. When you rotate it based on the axis, flip the numbers. Wherever the numbers are, just flip the numbers. You end up getting the other structure that you need. So this is how you can do it. Now, if you don't have 4 on the back side, what would you do? The first thing, when you have 4 not on the back side, on the side, then we rotate it horizontally. Now, if the 4 is on this side, we rotate it horizontally first and then check the structure. So here we are rotating it this way so that we change the structure. Now, the same way, you can always use this trick to adjust a molecule so that always the lowest priority one faces away from you. So with always the fourth priority group facing away, you can designate the configuration here as R. Notice that this is clockwise, so we can put a priority R. So let me let me give you a summary of the Cahn Ingold system. Number 1, identify the 4 atoms that are directly attached to the chirality center. Step 2, assign the priority based on the atom based on its atomic number. The highest atomic number 1 gets priority 1 and the lowest atomic number, which is often hydrogen, gets priority 4. If two atoms have the same atomic number, move away from the chirality center, look for the first point of difference. So the priority of the first point of difference differentiates the two atoms. And when constructing lists, compare. Remember that a double bond is treated as two single bonds. So step 4 is to rotate the molecule so that the fourth priority is on a dash. So make sure that always rotate it in such a way that fourth is always on the back. Next, determine whether the sequence 1, 2, 3 follows a clockwise or an anti-clockwise order. If it is clockwise, R. If it is anti-clockwise, yes. So this is how we can designate this. So in this structure, so this is the chiral center. Now let's try and designate the structures, the number. So first one, you have NH2, 2 and 3. And there is one another one that is not shown. If it's not shown, it's hydrogen. The hydrogen here is in the back. Now let's start giving priority for the numbers. Which one gets the first priority? So the largest one is nitrogen, so that gets first priority. Hydrogen is the smallest one, that gets the fourth priority. Now both here are carbon and carbon, but this carbon is connected to another carbon, but here this carbon is connected to oxygen. So here it is connected to carbon, here it is connected to two oxygens. So you have carbon, hydrogen, hydrogen. So now the first priority point of difference is carbon and oxygen. So oxygen gets the priority. So which means this becomes 2 and this becomes 3. So now write down the structure. You have 2 here, 3 here. So on the dashed part you have 4. On the on the wedge part you have 4. On the lined part you have 1. Now 4 is to be in the back. So which means that we rotate it horizontally. So rotate it horizontally. So when you rotate it horizontally, flip the names. So basically 3 comes on this side. 1 comes on this side, 2 goes on the other side, 1 goes on the other side. Sorry, 4 goes on the other side. So this stays the same, the wedge and the dash. Right, so 4 is already in the back. Now look for 1, 2 and 3 and connect them using a circle line. So it is anti-clockwise, so which means yes. So this chiral center has a yes configuration. So this is how you differentiate enantiomers. So by using the R and S configurations. So try these problems here. First thing is try to locate each of the chiral centers that are in the molecules by calculating the chirality. And second, try to identify the configuration of each of these molecules, whether it is R or S of each of these chiral centers. So pause the video right here and try to solve this problem. So we use R and S configuration in the IUPAC name just as it is. If you have one single chiral center, we write it based on, just write it as single R and S in front of it as a prefix. If you have more than one chiral center, represent it with its number and represent its chiral center. So the position, so always look at the locant and the chiral center if it is more than one. So if you have more than one chiral center, use the locant as well to represent the chirality of each of the positions that you are trying to represent. So the problems that you have done before, so try to name these compounds here. If possible, try to use the simple ones. So try to use B, A and E and try to find out their names. So pause the video right here and try to see if you can name these molecules. Next, let's discuss optical activity. So because the structures of these enantiomers only differ in some way, in the same way as your right hand differs from your left, they also have the same physical properties. So when you check the physical properties of the molecules, they look exactly the same. So enantiomers only differ in two ways. One, how they interact with the chiral compounds, and two, by their optical activity. So what does optical activity represent? So let's take a look at the example of polarization of light. If enantiomers generally have opposite configurations, which means they rotate the plane polarized light in opposite directions. So for example, if you have a particular light and if you're passing it through a filter that contains a particular molecule which has an R configuration, the plane polarized light will come at a certain angle, and if it is passing through S, it also does the same configuration, but the configuration here is perpendicular here. So here it becomes parallel. Notice that here the configuration will change based on what you are putting in front of the structure. So here we are using both R and R. Here I am using R and S filters. So when you use R and S filters, no light will pass through. So when plane polarized light is passed through a sample of the chiral compound, so the plane that the light travels on will rotate. So that is the idea behind plane polarization and how the optical activity changes. So compounds that can rotate the plane polarized light are called optically active molecules. Only chiral compounds are optically active and achiral compounds are not optically active. So one way to know this is by calculating the specific rotation. So enantiomers will rotate the plane of light equal degrees in opposite directions.
So the degree to which light is rotated depends on the sample concentration and path length of light. So for example, standard optical rotation measurements are generally taken with 1 gram of the compound dissolved in 1 ml of solution with a path length of 1 decimeter for the light. So which is given by specific rotation equal to alpha, so which becomes alpha by c times here. So we represent this in terms of alpha in the brackets representing temperature on the top and the wavelength on the bottom. So let's see a problem and let's see how we can calculate the specific rotation for any given molecule. So here the problem is given here is when 0.300 grams of sucrose is dissolved in 10 ml of water placed in a sample cell of 10 centimeters in length. The observed rotation is 1.99 degrees. Calculate the specific rotation of glucose. So wrote down the values that are given. So notice that, so first write down the formula for specific rotation. So specific rotation alpha is given by alpha by c times L. So alpha here is the observed rotation. C here is the concentration in gram per ml, and the last one is L, which is the path length of light, generally calculated in decimeter. So what is 1 decimeter? 1 decimeter is 10 to the power negative 1. So 1 decimeter is 10 centimeters. Now note down the data that is given in the problem. So in the problem the values given are, so observed rotation is 1.99 degrees. The concentration of the concentration is gram per ml is mass by volume. So mass is 0.300 gram by 10 ml. So you have 0.03 gram per ml. Path length is given as 10 centimeters. So when you convert it into decimeters, it's 1 decimeter. So how do you calculate the specific rotation now? So that becomes, write down the symbol as well. So 1.99 degrees by C here is 0.03 times 1. So that becomes 1.99 by 0.03. So let's try and calculate the value. So let's try and calculate 1.99 by 0.03. That gives you 66.3 degrees. So that gives you 66.3 degrees. So now we have the value that you need. So this is the specific rotation alpha. Now we have to represent it as, remember this representation. How would you represent it? So lambda here is on the bottom. Lambda is the D line of the sodium spectrum. So write down D, and at 20 degrees centigrade. So 20. So this is the value of the specific rotation of the molecule of sucrose. So plus 63, 6.3 degrees. So in the same way now, pause the video right here and try to see if you can solve these problems. So try to use these problems as examples so that it becomes easier for you to understand how to solve this problem. So pause the video right here and try to solve these problems. Next, let's discuss the optical activity in general. When you look at this, notice the R structure gives you minus 23. The S structure ends up giving you plus 23. This is a common reference to knowing optical activity. Chiral molecules have opposite signs with the same exact specific rotation. R and S configurations refer to the configuration of the chirality center, but plus and minus here, we represent that as the direction of the plane light that is rotated. And plus, whenever if your molecule gives you a plus positive specific rotation, we call it a dextrorotary. If it is negative, it's written as levorotary. So if the compound below here has a S configuration, that does not mean that it has to be positive, which means that this molecule, there is no correlation between R and RS and positive negative. But if you have R and S, if one is positive, the other will be negative. Or if the one is negative, the other will be positive. But it doesn't mean that R and positive negative have any connection with each other. So if one is 1, the other becomes the opposite sign. So it's optical. So notice that this molecule, even though it has yes, it has a lever rotatory configuration, but it is detrorotatory at 100 degrees centigrade. So depending on the temperature as well, it can change. So the optical activity is represented by its magnitude. So the magnitude and the direction of the optical rotation, we cannot predict it, so but we can only measure it experimentally. However, we can predict the rotation of racemic mixture. What is a racemic mixture? Racemic mixture is a 50-50 mixture of the two enantiomers. So if not, if we call this a racemic mixture because racemic mixtures have equal amounts of both R and S enantiomers. But if one enantiomer is present in excess relative to the other, then the mixture will have an optical rotation, but it will be less than the pure enantiomer. So this is represented by a quantity called enantiomeric excess. So enantiomeric excess is the value that gives you an understanding of which one is excess in a given quantity. So we represent it as percentage E. So the formula here is the observed value of the rotation by the specific rotation of the pure enantiomer. For example, when you take the molecule 2-bromobutane, so it has negative 23.1 and positive 23.1 specific rotation for R and S, but the mixture has negative 4.6. So which one you can find out which is enantiomeric excess here. So the percentage of enantiomeric excess can be given by minus 4.6 by minus 23.1 into 100%. That is 20% enantiomeric excess, which means that any one of R and S has 20% extra than the other. So that's how we can differentiate enantiomeric excess. So use that formula here. So let's try the first problem. Let me do the first one. So the specific rotation of L-dopa is minus 39.5. So a chemist prepared a mixture of L-dopa and its enantiomer. So the mixture has a specific rotation of negative 37. So this is the observed rotation, which is minus 37 by minus 39.5 times 100. So if you calculate this value, you should get, notice that both are modulus. So the top and bottom both are modulus, which means that all of them should always be positive. So 37 over 39.5 times 100 becomes 93.67%. So this here is the percentage E of L-dopa. So use this principle now and try to solve this and these problems. So pause the video right here and try to solve these problems.